All right, so we're going to start with a simple one-dimensional case where you got a mass distributed along like an axis. So think about this like the x-axis, where I have one mass, M1, another mass, M2. And the balancing point is where I would place this what they call a fulcrum, where I would place it so that it's able to balance. The mass 1 and mass 2, maybe they're different. They're at different distances away from this fulcrum. And based on mass 1 being D1 away and mass 2 being D2 away, we can find exactly where to place the fulcrum. Okay? Using Archimedes' law of the lever, we have that basically the product have to equal each other. M1 D1 has to equal M2 D2 in order to balance out. Okay, and that idea is going to be behind the scenes driving our formulas. Our formulas are going to be integration. Our formulas won't be 1D. Our formulas will be more involved. But this is what drives all of our formulas, this law of the lever. And so if I place 0 somewhere and I have this this M1 placed at some X1 and this M2 placed at some X2, then I'm in search of the place, I call it X bar, the place where I would put the fulcrum so that I get my balance to work out. And then my distances D1 and D2 become the distance from the center. X bar minus X1 for D1, but then X2 minus X bar for D2 in that order so that we get a positive distance. Okay, and then we're supposed to be able to multiply M1 times D1, and that's supposed to equal M2 times D2. If we multiply this out and solve for X bar, we'll have M1 times X bar, and we'll add over M2 times X bar, and then we have M2 times X2, and we add over M1 times X1. Factor out the X bar and divide, and this formula will be how we can calculate exactly where to place the center at, where to place the fulcrum at, so that it balances out. M1 X1, M2 X2, and then divided by M1 M2. This is behind the scenes. That law is what gave us this. This 1D will ramp up to 2D, and we'll see that the formula looks a lot like this. When we take M1 X1, M2 X2, and divide by total mass, M1 plus M2. Okay. So if I give you points on a line, we would do it like this. If I give you points out in the XY plane, then we have to figure out what to do there, and that's on the next slide here. But questions about this first? Is that okay? Understandable? Take what's in the box, basically, is what you should take away from this, not the derivation. Okay, this is all masses on a line. The points are in a line. They don't have to be that. But the numerator here is called the moment. There's two parts. There's moment for the first mass, and there's moment for the second mass. And it's these moments that get added up, and we divide by the total mass. And this idea in general will be how we will figure out what to do for our case when we end up trying to find the center of mass for a region in 2 dimensions. So point mass in 1D, you do it like this. Point mass in 2D will be on the next slide. Now, if I put more points, then still, I'll just be adding to the formula. So if I had a third point, then I just add on to the numerator and add on to the denominator. I add the moment of the third point, M3 times X3. I would add that third mass onto the total mass. So you're not restricted to just have 2 points on the line. Okay? And the totality of the numerator, that's the moment of the system. And so to get X bar, we get the moment of the system divided by the total mass in general. Okay. Moment of the first one, moment of the second one, and then the total moment of the system. Okay. So if I have a bunch of them, this is a summation of however many. This is n of them, a finite number, and I divide by the total mass. So if I have 3, then I could take all 3. I have 4. I can just use this formula to help me figure it out. Okay. Multiplying by the total mass, then what I get is basically an explanation that if the total mass were concentrated at that place X bar, then its moment would be the same as the moment for the whole system. The numerator on the left-hand side here, and if I multiply by total mass, I get the left-hand side here and the right-hand side here. This is the total moment of the system. And so this idea of okay, what I'm calculating by x bar is take all these masses, put them at one place. The total moment there is the same as the moment for the system, basically. We're looking for that place where I can place the entire mass so that I get balance, basically. And the moments would be the same. In 2D, I have an x and a y axis. And so I have distances from each of these axes. The points have coordinates x1, y1, x2, y2, x3, y3. And now I want to balance these. I want to figure out where to place my center at to balance on this 2D. Picture being in a plane and doing everything that we did from before. So I have a moment now about the x-axis, but I also have a moment about the y-axis. And so I call m sub y the moment about the y-axis, and it's supposed to measure the tendency of the system to rotate about the y-axis. And so it would be the same thing. Just multiply moments times masses. Okay, so the distance off of the x-axis, we've learned that already, is the distance off the y-axis is x, and the distance off the x-axis is y. And so if I want to get the moment on the y-axis, I got to use these x distances. But if I want to get the moment on the x-axis, I got to use the y distances. And so that's why the variables get mixed up like that. But the formula is the same. That would give me x bar, but now there's a y bar that I can calculate too. And that comes from taking the moment about the moment of the system to rotate about the moment of the system about the x-axis. And I use the same formula, but I change the x1s into y1s. And that y2. Okay. So this is the general formula. And it gives me a coordinate of a point. X bar, y bar. Okay. And then this idea is what we're going to take into 3D. I'm going to take infinitely many points. I'm going to take a region and try to figure out if this was a thin three-dimensional region, where would I place the balance at so that the system doesn't tip at all. These are the general formulas that are going to help me get it. Moment about the y-axis divided by total mass, that's x bar. Moment about the x-axis divided by total mass, that's y bar. Okay. And so if I give you it in 1D, we use the other formula. If I give you points in 2D, you can use this formula. In general, though, when we get our problems, we'll be having regions in the xy plane, and we'll have to integrate to get the answers. And so that's what's coming. And once again, the moment about the y you can multiply through, and the moment about the x you can multiply through. And this is what it means for the center of mass. It's where if you were to place all the mass, take these total mass, add it up, put all the mass at that one place, and you get the same moment as the system has. Okay. The place you would put it at. All right, so we have these formulas. We should do some examples. Let's see. Does our textbook have examples of this? That's a good question. Does our textbook have examples of what we just did? Or do they go right into the 2D? I think they have examples. 6.6 moments in center of mass. Exercises. Just using formulas. We got to figure out, make sure we're using the right formulas. No, so they skip over that and they go right to the actual heart of the matter is if we have regions in the XY plane. I guess later on they go back to it. Yeah. All right, good. So they have the 3D picture. They have some explanation. They don't do examples of it, but here's where we're headed though. We're going to take a region in the XY plane and try to find the center of mass for that. Let's see here. Okay, so it really is 3D. What happens is the third dimension is going to be some thin thickness. What we have is a plate. I have this region in the XY plane. Okay, and I'm going to consider it as like a film, like a thin film where I have some negligible thickness to it, and for this class we have to have, for this part of the class, we have to have the density be uniform. How the mass is spread about the film, I need for that to be some constant. Later on, when we learn triple integrals, we'll be able to relax that, or double integral. We'll be able to let this density be depending on where you're at on the plate. But for now, we have to have the density uniformly distributed across, so that one part of it isn't more heavy than the other part. And so I have this region R in the plane, and technically what I'm looking for is not a center of mass, it's called a centroid. But if you want to call it center of mass, that's fine. It's called a centroid when it's in this setting. And I'm looking for some X bar, Y bar. Okay, same idea as what's going on there. But basically, the idea is that I have this point here that I'm looking at, like we did before, cut it into subintervals and add up the all the subintervals, and you get the integral. And so that's where we're headed. Instead of going through the nitty-gritty of that, I just want to tell you that the formula is the following. I have this function y equals f of x, and this function y equals g of x. And it looks just like the picture we have here. So f of x is my upper function, my g of x is my lower function. Okay. And so it makes this region in the xy plane. Call it S in here. Density is constant throughout, just some constant rho. It ends up not playing a role at all in the formulas. And so to calculate the likelihood of the film, the region, the likelihood of the region to rotate about the x-axis, I can find that through this formula. Okay. Why is it this formula? It comes from the last slide of the description of how to calculate the center of a rectangle, the center of mass for a rectangle. So you have to square the, it's basically, it's kind of like a disc wash, it's like a washer thing where you take the distance up to the one squared minus the distance down to the other squared. Take half of that and integrate from A to B. That's your moment about the x-axis. The moment about the y-axis is different though. About the y-axis, you have this this radius x, and then the difference between the two functions. This is kind of like shells here. The first one's like washers, the formula for washer, and then the second one's like shells. You have this radius, and you have the height of the rectangle, the fx minus the gx, the height of the rectangle there. No squaring at all, and there's the radius is x for the moment about the y-axis. And the setup is still the same though. If I want to find x bar, I use m sub y divided by total mass. If I want to find y bar, I use m sub x and divide by total mass. The way I get the total mass is just by integrating, basically finding the area of the region essentially. Because the density is, mass is density times, but the area is essentially so mass is density times volume. And the thickness part of volume is negligible. And so we have this, it looks strange, but it says that mass is density times area, essentially. Because of that, we think of the thickness of it. Maybe if you want, just think of the thickness of it being 1. And so that formula for that you like for mass being density times volume, maybe that can then still hold if you have the thickness of it to be 1. Anyway, how do I get it? I go with the formulas that x bar is m sub y over the total mass, and y bar is m sub x over the total mass. And in both of these formulas, the density cancels out. I'm sorry, that's out of order there. So it's really 3 integrals you need. And then divide them in the right way. X bar is the moment about the y-axis divided by the total mass, and y bar is the moment about the x-axis divided by the total mass. So it remotes to just plug it in and chug it into the right formulas, unfortunately. And so we have, just to make sure that we don't get it confused, and the formulas are very different, but they both have total mass in the denominator. So it's essentially it's three integrals that we go find, and we divide them in the right kind of way, and it will find the exact center where we can, if we were to place it underneath the plate, we make sure that the plate wouldn't tilt at all. Okay, so we do m sub y divided by m for x bar, and m sub x divided by y divided by m for y bar. Okay. As long as the functions are reasonable, the integration shouldn't be too difficult. We don't know anything more than integration using U substitution, so or just find the antiderivative using power rule and reverse or trig or something. So these integrations shouldn't be trouble, and it's just a matter of setting it up. And so, questions on the formulas? Let's go ahead and then. Oh yeah, there's a question. Hand up. Yeah.
So the x bar is
Yeah.
really the moment about the y-axis divided by total mass.
Yes.
Just confusing the x is not one about y.
X is the distance off of the y-axis,
Okay.
and y is the distance off the x-axis.
Okay.
Yeah. So you got to use that to help you rationalize it. It's easy to get mixed up. Yeah. It makes sense to use mx for x and my for y, but it's the other way around. Yeah. Okay. All right. Let's see an example. My region is going to be between these curves, x minus x squared and negative x. My density is going to be some constant rho, won't play a role. So there's my line y equals negative x. And there's my line y equals, my curve, y equals x minus x squared. Somewhere there, I'll be able to find a place. If I was to give this some thin thickness and turn it on the side, there'll be a plate in that shape. And I'm looking for the place where I can balance the plate. Density is uniform throughout. It won't play a role. We'll go with our formulas from the previous slide. What we need are the limits of integration. Where's this thing start and end at? And so all the intervals are with respect to x, though. And so, they're going to cross at 0, and they're going to cross someplace else. And we just need to find that. So we set them equal to each other. And it's going to be 2, right? So, it's x squared minus 2x is 0, or 2x minus x squared is 0. So yeah, 0 and 2. Okay, those will be our limits of integration of all of our formulas. So remember the formula from x bar and the formula for y bar. They have different numerators but the same denominator. And actually the y bar, what I do is I push the 2 down in the formula. You don't have to do that, but it makes it a little easier for me. And I can just focus on, see the half. Where's the half at from that formula? Yeah, I just put the 2 down there. The half from this formula, I throw it down here in the denominator. You don't have to do that, but it helps for me. So I just concentrate on finding these 3 integrals, and I plug them into the right place. The purple, the blue, and the red integral. I go get those, and I just plug them in. So first up, let's go with the purple. X times the quantity f of x minus g of x. F of x is the upper function, g of x is the lower, so getting the picture is critical. So you know who is who. Let's work this out. It's just, hopefully it's not too much trouble. So we're talking about the integral from 0 to 2, x, and then the difference between these, essentially, where this guy is x minus x squared. That's what we'll call f. And this guy is negative x. That's what we'll call g. So x minus x squared, that's the f. And negative x, that's the g. F minus g from the formula. Okay. And it ends up as, simplifies to be 2x minus x squared. Because the minus is a plus. So what we're really integrating is these guys multiply. Let's go ahead and distribute. So 2x squared minus x cubed. That's all it is. From 0 to 2. This is a plug-in and chug. I'm sorry about this, but we have to go through it though. 2x cubed over 3. And x fourth over 4. From 0 to 2. So what are we looking at here? 16 over 3 minus 4? Yeah. I think that's right. So 4/3? That's not the answer. That's part of the answer. That's the numerator to x bar. In the end, I end up showing like a picture of it. You can see it's the kind of, well, since the density is uniform, it's kind of like the geographic center. If you were to place, place something right in the center, that's what we're looking for there. It's called the centroid. So we got 4/3 for that. All right, how about this other guy, the denominator? F minus g. This is the mass. This guy is the moment about the y-axis that we just found. Now let's go find the mass. Same limits, same subtraction of f and g. So let's use the simplified version of it. Just no x this time. That's all. So we get x squared. The 2 cancels with the division by 2. X fourth over 4. And we're going from 0 to 2. Oh, no, this is, oh, that's not, okay, this is easy. What is wrong with me? Slow down already, jeez. F minus g is 2x minus x squared. Sorry about that. Slow down. F minus g is the 2x minus x squared. Okay, right. It's x minus x squared plus x minus a negative x if you want. It's this guy here. So when we integrate, we get x squared minus x cubed over 3. Sorry about that. Um, 4 minus 8/3. So 4/3, but for a different reason. All right, great. So 4/3 for the moment about the y-axis, 4/3 for the mass. Great. All right, and then finally the numerator, the moment about the x-axis. This guy is m sub x. This guy is the mass, and this guy is m sub y. All right, so this time, so these are so much alike. This is very different. We have to square first. Okay, so we take x minus x squared and square. We take minus x and square, and then we subtract. Okay, so that is x squared minus 2x cubed plus x to the 4th. When you square that out. Now, when you square minus x, you get x squared. So from that, we're supposed to take away x squared. Still integrate from 0 to 2. So it looks like your x squares cancel. And we end up with minus x fourth over 2 plus x fifth over 5 from 0 to 2. Yeah, something like that. So we get, what's that, negative 8 plus 32 over 5. It's okay. It's a negative value. You'll see why. So we get altogether negative 8 fifths. Okay. Now, had mass been negative or had, we'll see why. Just look at when we go to the picture, we'll see why it has to be, sort of like a negative for the moment about the x-axis. Moment about the y-axis makes sense to be positive, but the moment about the x-axis doesn't make sense to be positive. Okay, so we get negative 8 fifths for that. All right, great. So then we have to find x bar and y bar. Remember, x bar is the moment about the y divided by the total mass. So it's 1. And y bar is oh, there's something skipped here. Sorry, there's a lot of stuff skipped. This is out of order here. Sorry. Y bar is the moment about the x divided by twice the mass. From the formula. Or take half of the moment about the x. Either way you want to do it. So negative 8 fifths, and if you double 4 thirds, you get 8 thirds. So the 8's cancel, and you get this negative 3 fifths. Here's a picture that shows why it would be the case. I think it's to scale too. I think the picture's drawn to scale here. Well, it's meant to be. Oops, sorry. Yeah, that would be the geographical center. If I was to try to balance that, I need to place the balance right there. The key, though, is that the density is evenly distributed. It won't be always that that possibility. For next time, when we later come back and revisit this, part of it will weigh more than the other part. There'll be more mass distributed in other places. And so then that's going to be a difficult question. But this is not that bad. It's just you sort of eyeball it really and kind of get a reason why your answer should be that. All right. It's not simple just finding the height and the low and taking the division. It's not that simple. It's just a lot more involved with it. So this is if it's between two curves. And everything gets much more simple if the lower curve is the x-axis. All the formulas that have g of x in them, basically the g of x would be 0, and so all the formulas simplify. And so I go through and give you all the formulas again for that situation. Okay. Sorry about the order here. But basically, all the g of x's that were there before, we had f of x squared minus g of x squared. G of x is 0 in this case. So you don't have to worry about that. X times the difference between f and g, no need for that. Just take x times f. Here, just take the difference between f and g, no need for g, just take f. And so the formulas greatly simplify if you're just talking about under a graph and above the x-axis, letting essentially g be equal to 0. Okay. So here, the g of x is equal to 0, and that just makes the formulas much easier to deal with. It doesn't change the formulas, it just makes them, it just drops off the g of x part. And don't forget this 2 is down here too. That just makes it easy to calculate. So you said g of x equal to 0 in the previous format. The animation is all backwards on that one. Sorry about that. Okay, so that should give you enough to make it through the problems that you have. Let me grab one from the text just to show you we're on point here. There's also some more to it, but I think that's good enough for us for now. So yeah, I can just randomly grab a question like So they do talk about varying density. I'm going to make you wait for that, though. So we're just dealing with questions 1 through 14. Let's go with let's go with question 13 for an example of the second type, where it's just between the function and the x-axis. So just real quick here, and we'll take a. That's what we have before with the g of x. That was under.
What if it's, under the x-axis? What if the f of x is 0? Just do the same thing.
Just flip them. Yeah. Just take all the formulas and set all the f's equal to 0 in that case, I guess. So we have our formulas from here. Let's go and grab those, put them on that slide. And let's just go work this out. Shouldn't be too much trouble. Your function is 1 over root x. And these are the formulas for x bar and y bar. Let's go get the 3 integrals necessary. So we have this function is f of x, and it's basically that g of x is 0. And so we're going from 1 to 16. There's m sub y, which is 1 to 16, x times f of x. M sub x is 1 to 16. Take f of x and square it. And the mass is 1 to 16, just f of x. 3 separate integrals. 16, that's a 6. I don't know where the 1 is, sorry. Yeah. 3 separate integrals, but so it's not that difficult. Take the x and the root x, that cancels to be root x. Integrate root x from 1 to 16. That's x to the half. So it's 2/3 x to the 3/2. So pull the 2/3 out. Don't put it in each of them. And take 16 to 3/2 and subtract 1 to the 3/2. What is 16 to the 3/2? You change 16 to be 4 squared. And then the square and a half cancel. It's the same thing as 4 cubed. Okay? So it is 64. And 1 to the 3/2 is just 1. So we get 63. But that's divisible by 3. 21 times. And so we get, what, 42. All right, great. Well, this one's going to involve a log. When you square a square root, you just get 1 over x. Now, that's going to be a log. Okay. So that's going to be the natural log of 16. Because the natural log of 1 is 0. And over here, this is x to the negative 1/2. When you integrate that, you get x to the 1/2, but don't divide by 1/2. Multiply by 2. And then we go from 1 to 16. 2 times the square root of 16 minus the square root of 1. So that's a 6. Now we have all the players. You gotta make sure we're careful with the formula, and don't forget this 2 in the y bar. X bar is going to be 42 over 6, more commonly known as 7. And y bar is going to be 42 over 2 times 6, because it is 2 from this formula. No, log 16, I'm sorry. Jeez, what's wrong with me? Slow down. Log 16 of over 8. Not much you can do to simplify that. I say leave it like that. That's good enough. X bar, Y bar, you're done. So it's just a calculation. I'm sorry. You just got to make it through it. The harder is if it's f of x minus a g of x. But this is much simpler to deal with when it's between the curve and the x-axis. G of x is 0. Question, yes?
Just in the first part, what happens at times whenever?
If I have x to the 1 and I divide by root x, it becomes root x. X times 1 over root x is the same as x over root x, which is root x. No? It's x to the 1 divided by x to the half. So you subtract, and you get x to the half. More questions, please. Don't be afraid to ask. Yeah?
Is it 2 times 6, 12, not 8?
Yeah, whatever you want to call it. Sorry about that. That was on purpose.